Hello everyone, my name is Mike. Welcome to our YouTube channel. In this video, we will explore conservation laws. These are fundamental laws that form the backbone of physics, engineering, and science in general. It is impossible to understand these fields without first understanding conservation laws. In fact, almost everything around us can be directly or indirectly described by these conservation laws. There are several conservation laws that one must understand to truly grasp physics, engineering, or science. In this video, we will focus on the conservation laws of energy, linear momentum and mass. Before we dive into these conservation laws, let us first look at two important concepts that are always used when defining these laws. Understanding these concepts will help ensure you are not lost when we reference them later. The first concept we need to it is a system. In the context of conservation laws, a system is any object or group of objects that we mentally separate from the surrounding environment. You can think of a system as an imaginary membrane that covers our object of interest. Everything inside this imaginary membrane is part of the system, and everything outside of it is part of the environment. For example, consider a car. We can define our system to be the entire car. In this case, the road that is in contact with the car is part of the environment since we have defined our system to include only the car. Similarly, the air in contact with the car is also part of the environment. We usually draw a line around the car to indicate that only the car is part of the system. Using the same example, if we have two cars next to each other, we can define our system to be only the first car, only the second car, or both cars. The point here is that a system does not necessarily have to include just one object. Understanding the concept of a system is crucial because once we define a system, we can study how certain quantities like mass, energy, momentum, and angular momentum change over time by measuring these quantities at the beginning and end of a time interval. Within a system, we can classify measurable or countable quantities into two categories, extensive and intensive quantities. Let me illustrate this with an example. Consider two cars standing next to each other. If we define our system to include only the first car, and we look at the quantity, number of cars, we find that it is 1. We can also look at another quantity, temperature, which might be 24 degrees. If we now expand our system to include the second car, the number of cars in the system increases to 2. However, the temperature remains 24 degrees Celsius. From this example, we define extensive quantities, quantities that depend on the size or extent of the system, for example, number of cars. Intensive quantities, quantities that do not depend on the size or extent of the system. Every quantity can be classified as either extensive or intensive. However, for the purposes of this video on conservation laws, we will focus only on extensive quantities. In fact, all the quantities we will discuss, mass, energy and linear momentum, are extensive quantities. In short, all conservation laws involve extensive quantities. The second concept we need to look at before going to conservation laws is a conserved quantity. A conserved quantity is any extensive quantity that cannot be created or destroyed. The value of a conserved quantity can only change due to the transfer of that quantity across the system boundary. Let me give you an example. Suppose we define our system to include a person holding a piece of paper. In this system, we can look at the extensive quantity, the surface area of the paper. If the person burns the paper, the surface area inside the system changes. However, if we consider the extensive quantity, the mass of the paper, we would find that the mass remains the same before and after burning. In short, a conserved quantity remains constant in an isolated system, a system where nothing enters or leaves. A non-conserved quantity, on the other hand, can change even when the system is isolated. Moving on to the main topic of the video, conservation laws, let us start by looking at conservation of mass law. Consider a system with objects inside it. They can be anything, cars, hair dryers, etc. The conservation of mass states that regardless of what happens inside the system, the total mass of the system will never change as long as the system is isolated. The only way to change the mass of the system is by removing objects from it or adding objects to it. Secondly, let us look at conservation of energy law. Imagine a system consisting of a moving, unpowered cart. From experience, we know the cart will eventually slow down and stop due to ground friction. This means that the initial kinetic energy of the system is converted to thermal energy due to the interaction between the cart's wheels and the ground. Because the system interacts with its environment, its energy changes. However, if there were zero friction, the cart would maintain a constant speed, and the system's energy would remain constant. Thus, energy is a conserved quantity that does not change in an isolated system. Thirdly, let us look at conservation of linear momentum. Similar to energy and mass, for an isolated system, linear momentum does not change. Using our cart example again, if there were no friction between the cart and the road, the cart would maintain its speed forever, and the momentum of the system would remain constant. The momentum of the system can only change if we introduce another moving cart into the system, thereby increasing the system's momentum. Otherwise, in an isolated system, momentum remains constant. In conclusion, conservation laws are the foundation of physics, engineering, and science. Understanding how mass, energy, momentum, and angular momentum are conserved in isolated systems allows us to describe and predict the behavior of physical systems. Thank you for watching. If you found this video helpful, please like, comment, and subscribe.